All right, thanks for reminding me, Yamin. Nice. All right, so sorry, the recording started a bit late, but for those tuning in, so I was just saying that, Brown representability tells us that, a certain class of functors, say a certain class of functors uh, on the homotopy category of CW complexes that are connected and pointed, right? So you need both of these hypotheses, is going to be representable. And now the exact things are first, you have this canonical map from the h of the wedge to the product of the h's, right? So you need that to be an isomorphism. And the second is this Meyer-Vittori's axiom, which is a bit of a mouthful, but basically a way to think about it is, if your functor was taking values in the category of something like abelian groups, then it basically says that you satisfy Meyer-Vittori's, right? So this is like the weakest Brown could. Also, actually, Brown in his original paper also had a condition of being countable on spheres. But it turned out that's redundant. You don't need that. But these are the weakest set of axioms under which you're gonna get that your functor is representable. So let's try to. We're gonna focus on the proof of this at first. So let's start. So one thing we're not gonna do is like prove the whole statement, because it turns out that then full proof is a bit disgusting. You have to glue together a lot of cells and then have a lot of technicalities. We're not gonna do that. We are, however, gonna prove like a weaker version of this. And before I show you the weaker version, let me actually motivate it. So in Brown's original paper, one of the very first examples he gave was ordinary cohomology being representable. And I think it goes without saying that this is a very important example, right? And what is it represented by? So it's represented by so let's say it's represented by some kn, right? And I want to compute what this kn is. So what I actually do is I plug in spheres into the functor, and we know the homology of the spheres, right? Topology 101, algebraic topology 101. So we know that it's G when n equals k and 0 when n is not k, right? So this tells us now what the value of this guy should be, and these are just simply the homotopy groups, because that's what maps from spheres to your spaces, right? And it's basically saying the homotopy group is G in this one place and 0 everywhere else, right? So, and it turns out that the spaces that satisfy these conditions are called Eilenberg-MacLane spaces, right? So we call them Eilenberg-MacLane spaces of type G, n, right? And this actually serves as a proof that these spaces exist in the first place, right? Because we know that cohomology has to be representable, right? And it's unique up to homotopy because of Whitehead's theorem, right? So we have this nice class of example just right out of the gate that cohomology is representable, but this is just ordinary cohomology. And as has been like the idea of this whole seminar, we kind of want to generalize that, right? So let's go ahead and do that. So now this is like the weaker version we're proving. And just one thing to note is that we're actually going to be proving the statement on the category of spectra, right? The stable homotopy category, not on CW complexes, although a similar argument will prove it for CW complexes. And I'm basically defining a cohomological functor to be the things that satisfy like Eilenberg-Steenrod axioms, basically, right? And this might be a bit different than what you have seen, but remember from like my last talk that you can derive excision and then like long exact sequence from this co-fiber sequence and then this thing, right? So this is really all you need. This is equivalent to the Eilenberg-Steenrod axioms. So the idea is that if you have a cohomological functor that satisfies these, this Eilenberg-Steenrod axiom on the stable homotopy category, then it's actually a representable functor in the stable homotopy category, right? So that's what it'll try to prove today. So before, hold on a second. So, what's going to be the idea, right? The idea is basically that, we're going to use spheres. We're going to start off, basically everything in my stable homotopy category comes from like the different sphere spectrum, right? You can like kind of glue the sphere spectrums together in a way to make everything else. It's analogous to how you use the spheres to construct every other CW complex, right? So that's kind of the idea. So we're going to first prove it for spheres, and then we're going to glue together the spheres to prove it for a general spectra. So before I move on to the proof of this, any questions so far? All right, let's go ahead. So, the first lemma I'm going to prove is that if you have a natural transformation between the two cohomology functors, and very quickly, a natural transformation of this type of functors, which are taking values in the graded abelian, in the category of graded abelian groups, a natural transform will have each of the individual elements be homomorphisms rather than just set maps, right? Just really quickly. So, if we have a natural transformation of cohomology functors, and its restriction to the spheres are isomorphisms, then the whole thing is an isomorphism, right? That's kind of what I said before, is that you prove it for spheres, you're done. So let's prove this. So first, for a spectrum X, we take something called the crude cellular tower. Okay, so what does a crude cellular tower mean? So first, you have this type of diagram whose limit is X, right? So when you take the co-limit of everything, it's going to go to X. And basically, the idea is that the mapping cone of all of these G maps, right? These are all co-product of spheres. And one thing I'm going to do in this talk is like I'm going to give you a statement for spectrum, but then I'm going to go down to the CW complexes for visual intuition. So let's do that. What does CGN being a co-product of sphere mean, and what does a crude cellular tower mean? So for X, a CW complex. For X, a CW complex, what you do is take Xn to be the n skeleton, right? Take Xn to be the n skeleton, and then you have a canonical inclusion, right? X0 includes into X1 into X2, but and obviously the limit of all of these is X, right? So what's the mapping? What's the mapping cone of one of these inclusions? Remember, for an inclusion, a mapping cone is just like xn plus 1 modded out by xn, right? But as you guys might know, what we're doing is like we're basically modding out all the boundaries. So at the end of the day, the only thing you have left is are just like the cells you attached for the n plus 1 skeleton, right? So it's a co-product of spheres. So that's kind of the idea. It's like a generalization of taking the skeletons, right? But if you guys think about it hard enough, you guys can see why we can form such a crude cellular tower, right? It's basically the analog of taking the n skeleton for CW complexes in spectra. So now that we have constructed that, the claim is that on all of these guys, my natural transformation is indeed an isomorphism. And you guys might be seeing the argument, like we make this like we break this thing nicely up so that at each step we're just adding in spheres, and then we kind of take the limit to prove equivalence. It's a bit more complicated than that, but that's basically the idea. And now oops. Right, so we're going to do induction as is usual for such things. So assume that eta xn is isomorphism, and we're going to prove it for xn plus 1. So we have this co-fiber sequence, right? And let me just write this down. So we have xn goes into xn plus 1, which goes into this guy, right? Remember the co-fiber sequence, and then you extend it by SAS into these things, right? So we have this co-fiber sequence, and we really only care about this part, which is why I wrote this part down. So you have this co-fiber sequence, which is just the co-fiber sequence generated by the GN, right? And you now apply both of the cohomologies to it, right? So I've applied both of the cohomologies to it, and note that I, instead of writing like, HK of SAS of xn or whatever, right? I just like use the fact that there's a natural equivalence between like hk of sus and just hk minus 1. So, no sus's in this diagram, fortunately. So, and this is the diagram you get. And then, you use the natural transforms to get this diagram, right? So now by inductive hypothesis, I know this guy and this guy are isomorphisms, right? So next thing, so this guy and this guy are isomorphisms. The next part is that, remember, CGN is a wedge of spheres or coproduct of spheres, right? And by hypothesis, we've said that you satisfy this isomorphism on sphere conditions, and H obviously splits over coproducts as was mentioned in the axioms. So this guy and this guy are also isomorphisms. And now by the 5 lemma, this is also an isomorphism, right? And hence by induction, we have proved that all of the eta xn are isomorphisms. And now we have like, sorry, let me go up here. So, now I've proven that all of the eta xn are isos by induction, right? Now we might be very tempted to just say, oh yeah, and then take the limit and cohomology, commutes with limit and we're done. But it's not quite like that. Unfortunately, we have a bit of a huddle, right? So, we have this, we have a natural map from h of, let's say, xn into the inverse, into the co-limit of the, say, h of x into the co-limit of h of xn, right? And it is very tempting to say this is an isomorphism. However, for cohomologies, this is in general only an epimorphism, right? So this is in general not an isomorphism, and so we cannot use the argument I just mentioned, right, to prove it for x. However, what we can do, right, what we can do is like think about the kernel of this map. If this is an epimorphism, to describe h of x perfectly, we're just missing the kernel of this. And this is actually a complicated thing done by Milnor. And we have this exact sequence to describe the kernel, but the lim0 is just the normal co-limit. So, what does lim1 mean? We're not going to worry about that today. The only thing you need to know is that lim1 depends only on the xn, right? And hence, like the natural map here would be an isomorphism. And same thing here, because this only depends on the xn, and we said that the natural transformations are isomorphisms on the xn, so they have to be an isomorphism here and here, and then you just use the 5 lemma again to get an isomorphism down here, right? And then you're done. You have showed that eta restricted to x is an isomorphism, and x was arbitrary. So any questions about this proof? Comments, anything? All right, let's move on. So, that's the end of that proof. So now we prove the big theorem that all cohomologies are representable. And so first we start by, we want to construct, so, for the naturality condition, we're actually gonna strengthen it a little bit, right? So what we're gonna ask is that, right, so you construct, so you want a representator E, sorry, Apple Pen, please work. Sorry. So you want a representator E of my functor H, but also you want a distinguished element of H of E, so that I'm defining the natural transformation between this representable functor and H by this thing. And what does this mean? Like, just plug it in, right? So eta EW would be from WE to H. And what's a map? Let's say F is a map from W to E. And we're gonna take that to H of F of E, because h of f is now a map from h of e to h of w, right? So that's all that's doing. And basically like this forces you to be a natural transformation. And the reason we're doing this is because it just, it just makes all the transformations nice and you can get the result nicely, right? So we have that. And also so actually let's go to the next slide. So first, remember in my last talk, I already told you guys that this representable functor is a cohomology theory, right? We already showed that. So we have a natural transform between two cohomology theories, and you can quickly check the way I defined it, that it is indeed a homomorphism component wise. So we have a natural transform between two of these guys. So all we need to show is that on the spheres they agree, right, by the previous lemma. And what happens when I plug in a sphere here? We get a stable homotopy group, right? So all we need to show is this kind of an isomorphism, and we're going to do this once again inductively. So first we start off with our E naught, which is going to be the co-product of all spheres for Y in SR and for all R. And basically the reason we're doing this is so that we basically always have this an epimorphism, right? Because we're just creating enough elements so that something maps in, if that makes sense, right? So this is like our first like rudimentary attempt to make this an isomorphism, is force an epimorphism but nothing more. So we're doing that, and then by the wedge axiom, it's we choose an element E naught of the product to be the product of all the Y's, right? Because we're distinguishing an element Y in each of these. And as I said, it's an epimorphism for every one of them, because by construction we have just created enough loops in so that for each Y there's a loop in E, right? And now basically we'll create a sequence of elements like this. Like at each step we're going to get a finer and finer approximation to E, and finally after taking a limit we'll get the actual E. So, and we also want some distinguished element, as I mentioned up here. And the distinguished elements are going to commute with the natural maps. So that's another thing I'm going to require. So how do we construct this? Well, so what you do is you take the co-product of all the spheres for everything in the kernel, right? So for all the Y in the kernel, and you basically create this kind of exact sequence. And remember, or co-fiber sequence, if you will. And remember, that just means that I'm taking like En, sorry. So I'm taking like En, and I'm modding out by all of these spheres, basically, right? That's what this guy really is, homotopy equivalent to. And yeah, so we're doing this. And what's the idea? The idea is that the kernel here are basically all of the elements of all of the loops of En that are disappearing in my map, right? And when I'm modding them out, I'm basically making those loops trivial, so in the next map they don't show up in the kernel. So this is kind of a way to get rid of the kernel. However, in getting rid of the kernel, we might have made some new elements in the kernel, right? So we have to do this infinitely many times. But that's basically the idea, where we notice we already have an epimorphism, right? So we already have a surjection, and all we need now is an injection. And the way to do that is by getting rid of the kernels, and we keep doing this forever. So we construct this forever, and now it turns out that, so now we use a nice argument to find the distinguished element, right? Because by construction, the En we had have hj En equals 0. Why? Because like literally we said these are the elements of the kernel, right? They have to be 0. And so by exactness, because remember, the co-fiber sequence gets sent to an exact sequence, we can pull that back up into something here. And so we have some element like this, whose image is En, and that gives us the new En plus 1, right? So now we have constructed En plus 1, En plus 1, right? And as I said, we keep doing this forever. So now we just take E to be the co-limit, right? And now remember I told you that cohomology and limit don't quite commute. However, they are surjective, and that's all we need, right? Because notice that all of these distinguished elements I made, since they commute with like the image of all the INs, they define like a class in the co-limit, right? So it's some element here is En, and I can just pull that back up into HE because this is a surjective map, and because it's and so I have some element E in HE, and now just by how I constructed it, this E and sorry, this should be SR. Yeah, and just by how I constructed it, like at each step, I'm like getting rid of the kernel, and it's still an epimorphism after each step. I've done this enough times to guarantee that what I'm left with is both injective and surjective, and hence an isomorphism. And so I have this. I have an isomorphism. And by the previous lemma again, isomorphism of sphere means that you're isomorphism everywhere. And hence this shows that there's some E that represents every cohomology functor. And that should be the proof of that. And by the way, most of this proof is from like a brilliant little book I found. So I've linked that if you guys want to check out more details later. So that's the proof of Brown representability that we're going to go over today. Any questions? Comments, anything? All right, let's move on. Right, so now, immediately by the Uneda lemma, we get that, natural transformations between two representable functors HK are two cohomology functors which are representable, right? So let's say one of them is representable by X, the other one's representable by Y. By the Uneda lemma, we know that the natural transformations of this guy corresponds to a map in the stable homotopy categories between X and Y, right? So we have this equivalence of categories between spectra and cohomology functors on spectra. This is a critical part that we'll get back to later. So in ordinary cohomology, we talk about cohomology operations being natural transformation between different cohomologies, right? But in the stable homotopy category, we prefer to talk about a different type of cohomology operation, the stable cohomology operations, which I believe we talked about in the first talk. And it's simply like something that commutes its suspensions. So if this diagram commutes, right? So we want this diagram to commute. That's the type of natural transformations we're interested in, right? So, and it's actually very easy to see because of this, that what you really care about is the zero component, right? We don't actually care about we only care about K0 or H0 because every other part of my transformation is like determined by this commutativity on the higher parts. So from that we can say that the stable natural transformations of HK is the same thing as just looking at H0 and K0, right? So we just want the natural transformation between these. And remember, H and K are functors to graded abelian groups. So H0 and K0 are functors to abelian groups. So we can still use like the Uneda lemma, right? And so by the Uneda lemma, this is the same thing as having the zero component of the morphisms between X and Y. So while all the natural transformations are determined by like the full Hom set, if you just care about the stable set, it's precisely the degree zero morphisms that you care about. So any questions on that? All right, let's move on to the next slide. Oh, it looks like I messed up a pause, whatever. So, the first thing to know is like, I think you guys can see like how my argument in the previous slide kind of pretty easily extends to CW complexes. You'd have to change a few things here and there, right? But it's essentially the same argument. At the end of the day, you prove it for spheres and then for everything else, but in CW complexes instead of spectra now, right? And so the same argument gives us that cohomologies are representable on CW complexes. So so we get that a cohomology is representable on CW complexes, and basically, so remember the suspension axiom that Hn of the suspension should be Hn minus 1. That basically tells us that sigma x of En is the same thing as x comma En minus 1, right? Where En are the representatives. But if you guys remember, by the adjunction of sigma and omega, the loop space functor, then I can actually make this like this, right? And now by the unit lemma, I get an isomorphism between this guy and this guy, or a weak equivalence, I should say, right? So we have this weak equivalence between the two sets, or between the two spaces. So, or in particular, I get a map like this, and hence I've defined a spectrum E, right? So, so the uptake is that I basically. And now basically, if I write Hn of x as the match between the suspension spectrum of x and then E, then it's easy to see that this is the same thing as this guy was, right? And and hence I have I've shown that every cohomology in CW complexes is indeed representable in the category of spectra, right? Which, if you guys recall, we did talk about this a bit in my previous talk. So now, obviously, if you have a map between two spectra E and F, then there's a natural transformation between the represented functor of E and the represented functor of F, right? So that clearly induces a natural transformation. Clearly induces a natural transformation of the different cohomology theories. So, and now you might be tempted to say that, oh yeah, by like the previous argument in the spectra, I can say that there's a equivalence of categories between category of spectra and cohomology theories on CW complexes. However, you'd be wrong, right? So let's see why. So I've induced like this natural map from EF star to the natural transformations of the cohomologies, right? And you might be very tempted to say, oh yeah, use the unit lemma. We know that there's a we know that they're naturally isomorphic, representable functors and the maps between the representatives. But here's my counter to that. Remember, we are talking about representable functors, but only on a subcategory of spectra, the suspension spectrums. We're not talking about being natural on everything. We're talking about being natural just on the CW complex part of stable homotopy category, right? So unit lemma does not apply. But you do still have this natural map from the maps between EF and the natural transformations here. And basically, in general, this is always surjective. So every natural transformation between E and F, the cohomology theories, is determined by a map between E and F, the spectra. However, it is not in general injective. This guy has a kernel, and this kernel is called, and members of these kernels are called hyperphantom maps. I will not work out an example of such a thing today. However, here's the Math Stack Exchange post with an example, if you guys want to check it out later. So yeah, the upshot is that while cohomology theories on spectra have an equivalence of category with spectra themselves, you don't have an equivalence of category in the case of just CW complexes, because this is a projection, this is not an isomorphism. Any questions on that? All right, moving on. So now we're very briefly going to talk about how we can extend this result to homology. I'm gonna prove to you that homology is representable in a sense, not always, but in a sense it's representable. And to do that, first we need a result of Adams. So so if you recall, the results we prove was that if you're like a cohomology on the entirety of spectra, or the entirety of CW complexes, connected, base, etc., but basically the entirety, then you're representable. But what if we just restrict it to finite CW complexes or finite spectra? Are you representable then? The answer turns out to be yes, and Adams proved that in one of his papers, right? So we're basically going to use this to prove the representability of homology. How? So first, remember Spanier-Whitehead duality. I know Adams is like X star in his book, but I do not like that notation at all. So we're gonna go with, I think, the more standard notation, which is dx, right? So remember Spanier-Whitehead duality is something that's defined only for finite spectra, right? That's why we're gonna need to use this, right? So basically, let's say I have a homology theory on finite spectra. Then if I apply the homology theory and compose it with like the Spanier-Whitehead dual functor, right? So something like this, then it turns out that this satisfies the cohomology axioms, right? Because it basically just like reverses all arrows and makes everything nice. So yeah, like Spanier-Whitehead duality allows you to go from a homology theory to a cohomology theory, right? And remember, we're still on finite spectra because that's the only place where it works. So now that we're on finite spectra, and I've just told you that cohomology on finite spectra is also representable because of Adams, well, just write it as something that's representable, right? So, I'm saying that this is representable, which is, say, H star of X, which is H star of D dx, because, double dual is just the same thing. And, H star of D is a cohomology, so it's represented by some spectrum E. So, it turns out that this thing is the same thing as maps from dx to E. But remember, like, the defining property of Spanier-Whitehead duality is that I can now move this into becoming this, right? This is like literally how Spanier-Whitehead duality is defined. So now it turns out that my homology is almost representable. It's representable in this sense. Now, a quick thing you might be wondering is, if I can do this with X, why can't I just move the E over here and make that a DE? And that would be valid, but only if E is a finite spectrum, because again, remember Spanier-Whitehead duality does not work for non-finite spectrum, right? So it's not quite representable in like the literal sense, but it is close to representable. But again, we're just on finite spectra, right? So we need to extend this to everything. And it turns out if you have a homology theory on like the full category, then it commutes with limits. This is like the one place where homology is a bit nicer than cohomology, is that it does actually commute with limits. This natural map is an isomorphism. So what you can do in general is like take your spectrum and take that as a limit of finite subspectras, right? And then basically plug in this relation, and you'll get that this also holds for an infinite spectra, right? And hence this shows that every homology is representable on the full category as something like this for some E, right? So in a lot of places, I've seen this formulated a bit differently, but they tell you that it's the limit of representable functors. And why is that true? Because remember, I told you that we cannot move the E over here because E is not finite. But there's a simple cheat code to that. Just take E to be the limit of finite things and then move those finite things over here by Spanier-Whitehead duality. And then you'll have like a finite list of, you'll have like a set of representable functors, and the limit of those are precisely going to be your actual homology, right? So that's like one way you could also formulate it. So any questions on that? I didn't really go into the details here because I don't think that's the main point, but any questions about any of these? All right, so let's go on. So so now let's go back to just our discussion of, so now we're going to make the same discussion for homology. Remember, by unit lemma for cohomology on spectra, there was a natural equivalence between cohomology theories and spectra, right? However, you don't have that here anymore. Even when we're considering homology theories on like the full category of spectra, right? You still don't have an equivalence of category. Like obviously, like a map from E to F is gonna induce a map from this guy into this guy, right? So obviously they induce a natural transformation between the different homology theories. But it turns out that this is in general just surjective, but not isomorphism, but not an isomorphism. So it's not injective. There's a kernel here. So, and like, why is that the case? Obviously we cannot use unit lemma because you're, performing this wedging thing, right? So you're not quite representable. You're a limit of representable stuff. You're losing information when you're taking that limit, so to speak. So yeah, this guy is, so there's like something in the kernel here. What are elements of the kernel called? So let me, yeah. So elements of the kernel are called phantom maps. Yeah, I know we had hyper phantom maps and phantom maps here. Like, I think originally people came up with the phantom maps as objects to study, and then like, and then like people discussed it for cohomologies where, where for like just normal spectra is already an isomorphism, so you don't have to discuss it in that much detail. But once you get to CW complexes, you have something like a phantom map, so they called it hyperphantom, right? But so phantom maps originate in homology, and basically it's telling you that the homology theories are not quite the same as spectra. There's a subtle difference of which are precisely these phantom maps, and the obvious thing to do is like mod out by the kernel, and then you'd get an isomorphism, right? So modding out by the phantom maps. Sorry, Apple Pen, come on. So modding out by the phantom maps gives you this set, right? So when you have EF and then F on the top, that means you have modded out by the phantom maps. So it's a quotient, and this is an isomorphism just because first isomorphism theorem, right? So the way we say it is like natural transformations are the same thing as this modified Hom set between E and F, and or I guess a quotient category of like stable homotopy category, if you will, right? And then again, if you want stable natural transformation or homology operations, if you will, you'd just take the zero component, right? And the zero component gives you precisely what you precisely the stable natural transformations. Of course, again, you have to mod out by the kernel, right? So that's a given. So any questions on that? And then lastly, I'm just gonna add like a final page just to talk about some miscellaneous things. So in his original paper, Brown proved that the functor that sends X to the set of all principal G bundles over X is actually a representable functor, and just a direct application of Brown rep. And the representative of this is called BG. If you have ever heard of that, that's what it means. And in particular, if you have rank n vector bundles, they correspond to UN, principal UN bundles. So all you need to care about is like to classify rank n vector bundles, all you need to care about is BUN, which turns out to be the infinite Grassmannian on of subspaces of size n. And also this is for like complex vector spaces, vector bundles. Obviously for real, you'd replace U with O, right? Orthogonal group instead of unitary, and C with R, but also real vector bundles are lame, so who cares, right? So that's like a quick example of Brown rep in action. And then it also turns out that Brown rep, so like if you think about the proof we did, right, it was almost like translatable between being on like the CW complex category and the stable homotopy category, because we use this like general ideas of like spheres, which in a sense generate my category, right? And like basically I used ideas like that, So it turns out that you have a general type of category called triangulated categories. Admittedly, I do not know much about them to speak in any details, but they're like a type of empty one category where where basically you have objects like spheres and objects like CW complexes or spectra, basically, and yeah, like basically the same kind of proof holds in that category also. So Brown representability holds. So this guy Niemann has a paper proving it, and sorry, and I highly recommend checking out his other works too, because he has like a lot of papers on like different versions of Brown representability and like a different type of triangulated categories. It's pretty good stuff. And with all that being said, that should be the end. I'm gonna